Hello, everyone. Welcome to the lecture on igneous rocks. And along with metamorphic and sedimentary rocks, igneous rocks are one of the three main rock types. And when we talk about igneous rocks, what we mean is that they're formed from magmas. So they're not weathered sediment that becomes rocks, and they're not rocks that have been metamorphosed by temperature and pressure. So they're rocks that form from a melt, from a liquid magma. And that happens in two ways. We get rocks that cool on the surface, and we get rocks that cool within the crust. And this lecture is going to cover, uh, sort of the main differences between those two igneous rock types. So what is a rock, and how is it different than a mineral? So, we in geology, we tend to be splitters more than lumpers. So we tend to want to classify things as finely as we can. That's different between different scientists. Some are lumpers, some are splitters. And what that means is sometimes people want to lump things together and put things together based on how similar they are, and then some people really want to parse things out and be as specific as they can and really separate things out. And both methods in science have their strengths and weaknesses. But in this case, we're differentiating rocks from minerals in that rocks are a lithified or a rocky aggregate, which means sort of a mixture of minerals, glass, and solidified organic matter. So over here on the right, we have a granite, and this is a rock. It's a intrusive igneous rock, and it's made up of primarily of these three minerals that you see down here at the bottom. Let me turn my cursor on. So when you look at a granite, you will see quartz. A lot of this darker stuff here is hornblende, and then the pinkish stuff we see is feldspar. So you have these minerals in your kits, and you're by now well on your way of kind of learning how to identify them. But when you look at a granite, you see that it's a combination of those things. And I encourage you to click on this link here and explore some of the different rock types. These are, and on this slide here, you see an example of each of the different rock types. We've got sedimentary rocks here and up here. Here's a metamorphic rock. You can tell by these beautiful folds. And then, you have a basaltic rock here, which is an igneous rock. You've got a granite here, which is an igneous rock. And then you've got minerals here. So geologists use these to tell a story about how that particular rock formed. Okay, so, and they're all very distinct. This metamorphic rock, which we'll talk about in upcoming weeks, has been deformed under high temperatures and pressures, usually in the base of a mountain belt. Here we have just a mineral, a metallic mineral, and that forms from melts too. But if this was combined with a bunch of other minerals, you would get a rock, right? And so here we have a felsic rock, and this tells us a story about where and how this cooled. Here we have this basalt with some little olivine crystals in it. They also tell you a story about where and how this rock cooled and formed, and what kind of magma it was sourced from. Here we've got a beautiful sedimentary rock with lots of bryozoan fossils in it. That also tells us a story not only about how the rock formed, but what the paleo environment was where these organisms were alive and thriving. And similarly up here we have these beautiful stratigraphy here telling us something about sea level rise and sea level drop, things like that, based on the different rock types that are there. So we're going to cover all of this in our sort of middle rock section here that we're working on in the next 2 weeks. So let's dive into igneous rocks. So a good place to start is to think about the environments in which the different rock types form. And I like to kind of separate this out in my head this way. It helps me kind of keep track of how rocks form based on the material that they're made out of and how that material is sourced. And so this is a diagram of the rock cycle. So these are our three main rock types here: igneous rock, sedimentary rock here, and metamorphic rock. And This is an important diagram. You're going to see this in the future in this class, and I just want to point out that in a good way that I like to think about it is igneous rocks are sort of like the first rocks to form. Okay, they would have been the first rocks to form as the planet was cooling, especially if there wasn't any real atmosphere to speak of, or a weak atmosphere, or an atmosphere that maybe had slightly different composition early on. It's much more carbon dioxide rich. And so you wouldn't have got a lot of weathering, right? There wasn't any running water early on in the Earth's history. There wasn't any atmosphere to speak of that would have done a lot of erosion and oxidizing. And so sedimentary rocks came later. And then with the advent of plate tectonics, metamorphic rocks would have come later. So the very first things to form on the Earth would have been igneous rocks. And that's just magma cooling and forming a crust. So lots of volcanism and lots of plutonism, or rocks cooling in the crust, so not erupting on the surface. And so igneous rocks, in my mind, are sort of step one. But you'll notice that there's an arrow going to igneous here from metamorphic. So metamorphic rocks are being pressurized and heated up. And if they don't become completely liquid, they'll form a metamorphic rock where they're just altered, or something we call metamorphosed. But if they are under so much pressure and high temperatures that they completely melt, they're going to cool to form an igneous rock again. So it is this kind of big circle, but you'll see that there's also other arrows where we can kind of jump between. So igneous rocks rise up through the crust from the mantle, and they either cool in the subsurface or deep in the crust, or they can erupt on the surface and cool quickly. And when magma is in the crust, we call it magma. And when it erupts on the surface, we call it lava. But you can think of them as sort of similar things, liquid melted rock. And then as they cool, they either cool as lava on the surface. And so we have a certain type of rock, igneous rock type, that is indicative of cooling quickly on the surface. And then we have igneous rock types that are indicative of slow cooling inside the crust. And then, of course, the atmosphere will the atmosphere will weather these things, whether it's wind erosion or water erosion, and those things become sediment, and they're transported around by water and fill in different basins and travel around and become sedimentary rock here, where they're buried under pressure and lithified. And then when continents collide or spread apart, you get metamorphic rocks based on those temperature and pressure regimes that alter the rock. So for the formation of igneous rocks, as I've said, they're sourced from magmas. So as magmas cool, they form bonds. Those bonds form minerals, and those minerals are solid. So as magma cools, it solidifies. And the way this happens, you'll remember from subduction zones, as one example, you get a partial melting of the mantle, right? Either that's through subduction, like I said, where there's an introduction of volatiles like water and gas that releases the pressure and causes that mantle to suddenly melt to a liquid, like a true liquid. And that makes it more buoyant because it's hotter and it's more fluid. So it's going to rise up through the crust, okay, in the form of magma. And then if it erupts on the surface, it will erupt as a lava. So those are the two main types. We have extrusive. So I like to think of the word expel. So like the earth expelling magma out onto the surface. That's extrusive. And that's where we would use the word volcanic. So volcanoes are eruptions of magma on the surface as lava. So that's volcanoes. And then we have intrusive. So that's in the crust. And that's magma that's cooling slowly. It hasn't erupted on the surface yet. It still could. But while it's cooling in the surface of in the crust of the earth, like below the surface, we would call that a plutonic rock. And those are intrusive. And here's a picture illustrating that. So The mantle would be somewhere down here. And so as magma is moving up through the crust here, it forms what we would call a magma chamber. So that's just a pocket where that magma is, and these can be huge. I mean, I think there's a pluton in Wisconsin that I looked at in grad school that's basically about a fifth the size of the state. So they can be huge, hundreds of square kilometers. And then also that magma chamber is still liquid, right? And it's slowly cooling, so it's precipitating out, remember, olivine first, and then pyroxene, and then hornblende. So that stuff, and by precipitating, I mean that stuff is forming bonds, becoming solid, and then sinking to the bottom of the magma chamber. And that hot material will continue to rise up through the crust in smaller amounts, thankfully for us surface dwellers, and that stuff can get into sedimentary layers, either horizontal to the layer, or parallel to the layer, or perpendicular up through the layer. And then once it erupts on the surface, excuse me, once it erupts on the surface, then it forms a volcano and lava flows, okay, and all sorts of debris and ash and smoke and all sorts of other things. So this would be an example out here of an extrusive feature with the lava flow, and this would be an example of the intrusive feature. And one thing to notice here, the shape of the layers here in this volcano, these are just lava flows that subsequently layer on top of each other. And so that's when you see a volcano, generally that's what you're seeing, is just lava flows that cooled, and then lava flows that erupted over those and then also cooled, etc. So what is magma made of? And this is important because this is what forms minerals and subsequently forms rocks. And so I've listed here kind of the I think 10 or so major constituent elements that compose magmas. And number one is silicon, common in most crustal rocks, oxygen, aluminum, potassium, sodium, calcium, iron, magnesium, and then gases like water and carbon dioxide. And these things would be gases in the magma because of the heat involved, right? So this stuff is in the gaseous phase, the higher temperature phase of a liquid. You can have liquid water, obviously, we know that. You can also have liquid carbon dioxide, but in this form, they're gases. And I have some examples of each of those here. These are there's our gas bubbles up there, and then oxygen obviously is a gas. But then aluminum, potassium, sodium, calcium, iron, and magnesium, here they are in their sort of metallic forms, in their solid forms. And magmas generally at temperatures of 700 to over 1,000 degrees centigrade. And what happens to magma as it starts in the high temperature zone, where it's still molten and the atoms are disordered and moving quickly? They're not forming bonds, they're just whipping around in there because it's hot, and that excites the ions in the magma. It starts in that phase, and then as it starts to cool, we get crystallization. So the atoms start to slow down, and they start to form bonds and arrange themselves in crystalline structures, which we talked a little bit about in the minerals section. For a great visualization, I highly recommend clicking on this link here. You can go into the PowerPoint slides on Blackboard, find this slide and click on that crystallization, because it gives you, it's a really great sort of simple cartoony way of showing you how this process occurs. And as you get crystallization, these magmas start to form minerals, and then those minerals go on to form rocks, specifically igneous rocks. And we tend to group these different crystallization processes into temperatures that range about 200 degrees centigrade. So from about 1200 C to 1000 C, we see certain minerals forming. And then at 1000 C to 800 C, we see certain minerals forming. And then from 800 C to 600 C, we see certain other minerals forming. And this is as the magma is cooling, minerals that are rich in calcium, iron, and magnesium are the first to crystallize. That's your olivines, your pyroxenes, things like that. And that stuff crystallizes first and sinks to the bottom and uses up a lot of the supply of those minerals, or sorry, those elements or atoms, uses up a large supply of those in the formation of these early minerals. And so there's less of that material in the magma as it continues to cool. So we see less iron, magnesium, and calcium in the melt. And this, as it's cooling, and that's because the bonding of those certain elements to other elements is favored preferentially based on temperature. So early minerals form at higher temperatures, sink to the bottom as solids, and then the next solids form, and they're made of different elements that like to bond at that medium range temperature. And those are going to be like calcium, sodium, still with some of that magnesium and iron. So that gives us like our hornblends, and we're starting to grade towards more sodium-rich plagioclase, feldspar, and then that process continues until the end, when all you have left really is a bunch of silica, which loves to bond at low temperatures. And so that's when you start getting the quartzes and the micas and the potassium feldspars, and also the continuation of the sodium-rich plagioclase feldspars. So one example here is a silica and oxygen bond, which forms that silica-oxygen tetrahedra, which is the basis of all the silicate minerals. And the way things tend to grow in a magma chamber is you get like a little seed, just a couple little atoms bonding, and then that creates the process where those crystals will just continue to grow. So a magma at any given time is usually a combination of the liquid component, so anything that hasn't solidified yet, it's still hot enough to be a liquid. Some solid components like silicate crystals, but also like olivine crystals, which is a silicate, but some of the simpler silicate crystals, and then as it cools, you get the more complex silicate crystals. And this is because, if any of you are taking chemistry, you'll know, but it's also discussed in the textbook. When you form a bond, that's what we call an exothermic reaction. So it's giving off energy in the form of heat, usually, but sometimes light. All of these things are electromagnetic energy. And so as you form a bond, you're expelling energy. It takes energy to break bonds, and when you make bonds, it gives off energy. And a way I like to think about this is, if I want to break the water atom up into its gas form, that is, break up the hydrogen and oxygen, I have to put it on the stove and turn on the heat. So heat will go in and break those bonds. And similarly, when I'm freezing water and I'm making those bonds stronger in water and making them form into a solid, essentially that's giving off heat. So that's why you have to freeze water in a freezer, because that's basically sucking up that heat, if you can think about it like that. And then you also have a gas component, so the volatiles. So we have water vapor, carbon dioxide, sulfide gas, etc. So the magma is a mixture of melt plus crystals plus volatiles at any given point in its cooling. It might have more crystals than melt as it's down in those lower temperature ranges, or it might have more melt versus crystals if it's at higher temperatures, and volatiles as well. So to get magma to a volcanic igneous rock, it has to erupt onto the surface and cool very quickly. But it might have been cooling slowly before it erupted, so there might be larger crystals. So a way to break that down is The stuff that cools very, very quickly doesn't have time to grow any large crystals, so it's you know, a finer grained igneous rock. And when we see a mixture of that over here on the right of larger crystals and ground mass, we call that a matrix. And so the stuff that cooled very quickly is this gray material that you see surrounding these larger, looks like plagioclase crystals. So that we would call the matrix or the ground mass, okay? And that's the stuff that cooled when it erupted. The stuff that cooled before that we call crystals or phenocrysts. And they were already solidifying in the crust before the magma erupted on the surface as lava. And so those are chunks of rock or chunks of minerals that have actually been able to start to grow some larger crystals. So, so you have the matrix, and then you have these crystals we call phenocrysts. And then you have gas bubbles or vesicles, and those are gas components that were in the magma that when they erupted onto the surface as a volcanic igneous lava, forming eventually volcanic igneous rock, that gas gets released and it leaves a void space behind, and we call those vesicles. And that's a vesicle there. So again, like I've said, the one main type of igneous rock of the two major types is rocks that are cooled at depth, and we call those plutonic igneous rocks. And they're made of mostly crystals. Okay, so it was cooling slowly in the earth, so that allows more time for bonds to form at the different temperature ranges as it's cooling. And so those crystals have time to grow. So if you're holding one in your hand, you can look down and you can see very distinct, you know, in hand sample to the naked eye, you can see distinct crystals of, say, pyroxene or potassium feldspar or quartz in the case of this granite down here. So where do the gas and liquid components go? Well, when that's happening, a lot of times, if it's not erupted on the surface and it's just cooling slowly, a lot of that carbon, a lot of that oxygen, a lot of that hydrogen just gets incorporated into the crystal structure of different minerals, okay? So certain minerals like biotite or muscovite, the micas, they tend to have a lot of water in them. We call them hydrous minerals. And that means that they have a lot of hydrogen and oxygens in their crystal structure. So those volatiles, because they're just ions in a melt when the magma is still liquid and super hot, they don't form carbon dioxide and they don't form water. They're just oxygens and hydrogens and carbons just floating around with all the other elements like aluminum or iron or magnesium or silica. And so they don't form those gases like we see on the surface. They just incorporate into the crystal structure, and you'll get, you know, a magnesium and a sodium and a bunch of hydrogens and a bunch of oxygens, and those form those hydrous minerals. And one beautiful example of a plutonic igneous rock is here in Yosemite. This is Half Dome, I think, and real famous for rock climbers. And it's a solid granite, and it's been exposed to the surface, and it looks like we see it as these big, beautiful cliffs. But this would have formed deep in the crust at some point, millions and millions of years ago. And we use this to classify igneous rocks. And when we're looking at crystal size and shape, we call that texture. So that's the size, shape, and arrangement of the different mineral constituents in a rock, okay? So when you're holding an igneous rock in your hand, the first thing you're going to look at is, are there crystals I can see? As in the case of this intrusive rock down here. Are the crystals so small and fine-grained that I don't see them and I see sort of a uniform color with no distinct minerals present, like we see here in this basalt, right? We know as geologists what's in this basalt, but none of that stuff was cooling slow enough for us to see crystal growth. This erupted on the surface, either in the ocean or on land, and therefore cooled very quickly. And so the crystals are still there, but they're so small we can't see them with the naked eye. We'd have to look under a microscope. And then was there gas in the magma as it cooled quickly, and did that gas leave behind these vesicles? So these are the three textures that we see. And the controlling factors on texture, again, like I said, is the rate at which the magma cools. Did it cool fast or did it cool slow? The amount of silica present, which we would call its composition. So did it cool at higher temperatures? So it's a little lower in silica, or did it cool at lower temperatures where there's a lot of silica? And the amount of dissolved gases in the magma. And again, I'm going to beat a dead horse here, but I really want this to sink in. Slow cooling, large crystals like this granite. Fast cooling, smaller crystals like this rhyolite here. And very fast cooling like this glass. And the words we use for those, and I apologize for them being so small in this, but when it's cooling at a very slow rate and we have coarse-grained large crystals, we call that porphyritic. When it's cooling very, very fast and we have the small crystals, we call that aphanitic. And when it cools very fast, we call that glassy. So aphanitic is fine-grained. Again, it's magma that solidifies at or close to the surface, so fast cooling. And the crystals are too small to be identified with the naked eye. Then we have phaneritic, or porphyritic in some cases if they're really big. And that's coarse-grained, so that's magma that crystallized slowly, producing an interlocking mass of coarse-grained minerals like this granite here. And while the last slide showed us phaneritic rock, and that just means crystals that are visible to the naked eye, so an intrusive, slow-cooling rock, we also get rocks that have different phenocrysts of different sizes, and that tells us something about how the magma was behaving in the crust. And in the case of this andesite over here on the right, we had phenocrysts of plagioclase forming, and then all of a sudden that magma erupted. And so then we get this finer grained ground mass or matrix surrounding these larger phenocrysts. But also we have this granite down here. And what this is telling us is, you'll notice we've got these really large hornblends here, or sorry, not hornblends. We've got these really large feldspars here, these potassium feldspars. But then we also have some hornblende here and we have some quartz here. And what this tells us is that the magma rose up to a certain depth, right, a certain pressure and temperature zone, and it started to form hornblends, right? If we look at the Bowen's reaction series, we'd see hornblends start to form at the hotter temperature. Then it rose up to a depth where it started to cool really slowly, and it hung out there a little bit longer than it did anywhere else. And so we get to the range where feldspars start to form, and these feldspars were allowed to cool for a much longer time and use up more silica and other ions, namely potassium, to make potassium feldspar. Then that magma rose up even higher in the crust, closer to the surface, and we started to get some quartz, but it didn't hang out there long enough to form large quartz crystals. It just formed quartz crystals about the same size as these earlier hornblende crystals, and then it was totally cool at that point, right? So no more magma to source any more elements from, and so we get, a short time at depth, a long time at some point in the surface to form these feldspars, and then a short time before it was completely cooled that gave us these quartz. And then if magma erupts onto the surface in the form of lava and then it cools super quickly, and that's usually because it ran into water, right? We see these glassy structures, and here they're glassy because they have no crystal formation whatsoever. All right, uh, they kind of look like plastic or glass, and uh, that means that there was just no ordering of the ions at all. They're just kind of frozen in that spot they were in when they were liquid. So they don't form any crystalline structures. So we think of them sort of like a frozen liquid, right? And that is because that lava just erupted uh, onto the surface as a lava and then just ran into like the ocean or a lake or a river, and it just flash solidified it really quickly. And so we see a lot of this glassy textured stuff at coastlines in volcanically active areas like Iceland or uh, Hawaii, places like that. So another type of igneous texture, you can get a pyroclastic texture. So that's when the eruption on the surface at a volcano is so strong that it actually blows the magma apart into small fragments, and then those small fragments cool very quickly because they're in much smaller particles, and they have more surface area to cool very quickly. And that's the case in the pumice that we have in our rock kits. Or they can be vesicular, which is a term we use to talk about rocks that have gases trapped in them in the magma. And then as they form, those gases are released and eventually, and they form these vesicles or kind of spaces, void spaces where there used to be bubbles. So aside from textures or crystal size, we also have the composition. And we use that also to classify igneous rocks. And 98% of the weight of all minerals at the surface are composed of silica, oxygen, aluminum, calcium, sodium, potassium, iron, and magnesium. Those are the 8 most common elements in the mantle and in the crust. Magma cools, crystallizes, forming the more iron, magnesium, and calcium-rich minerals, which we call ferromagnesian. And those are formed at the high temperatures, like we've talked about, or silica, oxygen, aluminum, and sodium. And those we call the non-ferromagnesian silicates. So ferromagnesian minerals are low in silica, high in those other 3, and they include olivine, pyroxene, amphibole, and biotite. And these are characteristically darker in color. And then we have the non-ferromagnesian minerals. They're higher in silica and lower in those darker elements. And so they're lighter in color, and they include quartz, plagioclase, which is sodium rich, and potassium feldspar, along with muscovite. So here's a ferromagnesian mineral. Here's another ferromagnesian mineral. This is plagioclase feldspar. It's calcium rich. It's actually called labradorite. And then we have this olivine here. And then here we have a plagioclase that's high in sodium, which we call an albite, and that's lighter in color. So that's an example of a non-ferromagnesian silicate. Igneous rocks are based on the proportion of these darker, higher temperature minerals and lighter, lower temperature minerals. So when they have more lighter minerals than darker minerals, so that is more quartz, more feldspar, like potassium feldspar and sodium-rich feldspar, and muscovite, we call those felsic. And again, that's based on lower temperature crystallization, so much more silica than anything else. So it's lighter in color, and therefore it's higher in proportion of silica, usually about 70% silica by weight. And then we have the darker rocks, which we call mafic. So they're 50% silica or less by weight. And they have less silica, even though they're still silicates, they have less silica overall, and much more of the ferromagnesian minerals like olivine, pyroxene, calcium-rich plagioclase, and biotite. And so those are darker. And so these examples here, we've got a gabbro on the right. So that's a intrusive or large coarse-grained crystal mafic rock. And then over here we have the lighter rock, which is a granite, and it's also intrusive, right? It has crystals you can see with the naked eye. So that's a felsic rock. And these vary in color. They also vary in density, which we learned on day one with the difference in densities between a granite and a basalt. So if you're looking at a lava flow, we get felsic lavas, so high silica lavas on the surface of the Earth and on, in the continents on continental crust. And we also get mafic lava flows at the surface. So what's the difference? What do you think would control the difference? Well, it's the amount of silica, basically. And the three major compositional groups, again, like I said, mafic and felsic. And then we also have this kind of in-between zone between 50% and 70% silica composition, and that would produce what we call an intermediate rock. So here's a mafic rock over here on the left. Here's an intermediate rock here in the middle. So it's about 50-50 or so felsic and mafic. And then over here you've got a felsic rock, which is lighter in color. Here's a great table to kind of show you that. So this row here is chemical composition. So felsic or higher silica, we would call that granitic. Intermediate, that would produce an andesite, and then mafic, that would produce a basalt. And then we also have ultramafic, which are less common these days. They don't really form now, but there was a time, about a billion years ago, 2 billion years ago, 3 billion years ago even, the Earth was hotter than it is today. And so it forms what we call ultramafic minerals, and those are mostly composed of olivine and pyroxene entirely, right? And we don't get those so much now because the Earth is cooler than it's ever been in its history. And so now, sort of the hottest temperature of formation minerals and therefore rocks that we get are generally mafic. And here's a nice little gradation of rock color based on percentage of dark to light minerals. And in the felsic zone, we have a lot more light minerals than dark. Intermediate, we have about 50-50. Mafic, we have more dark than light. And then ultramafic, mostly dark with just a few lighter minerals. And when these erupt on the surface or cool in the crust slowly, when they do that, we call them phaneritic or coarse-grained, and that's a felsic version of that is granite, intermediate version of that is diorite, mafic version of that is gabbro, and ultramafic version of that is peridotite. Or they erupt on the surface and cool quickly, so they're fine-grained. The felsic version of that is rhyolite. The intermediate version of that is andesite. The mafic version of that is basalt, and the ultramafic version of that is komatiite. Komatiites are quite rare, and fun fact, they tend to hold a lot of diamonds for whatever reason. Then we have porphyritic, and that precedes any of the above named rocks whenever they're appreciable phenocrysts, so differences in crystal size, drastic differences. So coarse-grained and fine-grained in the same rock. We call those porphyritic. Then again, the glassy ones, like I talked about, when that's compacted glass, we call that obsidian. And then when it's frothy glass, we call that the pumice. And then you can also get pyroclastic or fragmented rocks. And one is a tuff, and that's when the fragments are smaller than 2 millimeters. So this is usually like volcanic ash that solidifies into rock as it gets buried and fused together. We call that a tuff. And then we have volcanic breccia, and that's when you have fragments that are greater than 2 millimeters, and those form from the actual explosive eruption of a volcano on the surface. So, and they can have different compositions based on the composition of the magma, whether it be felsic, intermediate, or mafic. So here's a nice phase diagram that can help us sort of break this apart a little bit. And when we're looking at the different compositions, we've got felsic, intermediate, mafic, and ultramafic. This is a nice phase diagram that shows us that as silica increases over here to the left, so from hot to cool, potassium and sodium also increase to the left, whereas iron, magnesium, and calcium increase as we move to the right, and the temperature increases as we move to the right, so the temperature of formation. So for mafic rocks, we can just go to this mafic column here. There we've got our gabbro, which is our intrusive mafic rock, and our basalt, which is our extrusive or surface erupted mafic rock. We see high amount of calcium-rich plagioclase feldspar, a lot of pyroxene, and some amount of amphibole, and then some small amount of olivine here, right? Whereas the ultramafic, a little bit of calcium-rich, but mostly composed of pyroxene and olivine. So this shows you as you move down in this column that these are the minerals that are present at those temperatures and pressures and amounts of silica and amounts of iron, magnesium, calcium, etc. So a mafic rock is mostly composed of these 4 minerals. For our intermediate, we see there's our intrusive intermediate rock, diorite, and our extrusive intermediate rock, which is andesite. And that's going to have a lot of plagioclase feldspar. You notice that in your rock kit. Andesites have those big phenocrysts of feldspar. And then in the case of an andesite, which is extrusive, then it erupted, and the amphibole and pyroxene make up most of that darker ground mass that we see. And then the felsic compositions, which we also call granitic, we get the granite in the intrusive and the rhyolite in the extrusive or erupted. And we see in a granite, for example, we'll see quartz crystals, we'll see potassium feldspar crystals, we'll see sodium-rich plagioclase feldspar. Then we'll start to see the micas, muscovite and biotite, and we'll see amphibole, and that makes up a majority of the darker colored minerals that you see in lower amounts in the granite or the felsic rock. And then if this same chemical composition of magma was to erupt on the surface and cool very quickly, that's how we get a rhyolite. And as we go from mafic to felsic compositions, at the felsic end, we have lower temperature melts, right? So lower temperature formation of minerals, and those minerals are higher in silica, and therefore they increase viscosity. So when we say viscosity, that's a term we use in chemistry and in geology and in engineering. That's when a fluid is resistant to flow. So resistance to flow means thicker, flowing more slowly, and so we would say it's highly viscous or has a higher viscosity. And an example of that would be honey, right? Honey has a higher viscosity than water, which has a lower viscosity, because water has less resistance to flow. It wants to flow more easily. So it's, and usually magmas with higher viscosity have more silica in them, and they're cooler or at a lower temperature. So I wanted to show you this table again because based on viscosity, I want you to think about felsic rocks when they're on the surface as a lava. You get a rhyolite, right? A felsic lava. And that rhyolite is going to flow more slowly then an intermediate andesite lava, and a mafic basalt or basaltic lava, or a komatiite ultramafic lava. And this affects how volcanoes form, how they erupt, and what their eruptive materials, in what way they behave, right? So if you're near a volcano that is mostly felsic, or its magma is felsic, so it has high silica, right? That lava is going to form more slowly. And if you're at a mafic eruption, like in Hawaii, you get a basalt, and that flows more quickly. So this is like those lava rivers that you see, whereas rhyolite lavas are a little less common, and I'll explain why that is in upcoming lecture slides. So let's get into the actual rocks that you have in your kit, igneous rocks you have in your kit. The first one you have is a granite. I think that's number 24. That's a felsic rock with coarse-grained phaneritic textures with large crystals of potassium feldspar quartz, and then possibly muscovite, biotite, and hornblende, which is our amphibole rock that we have, or mineral that we have in there. And they can be porphyritic with large phenocrysts of feldspar. We call that actually, this won't be on a test or anything, but just for your info, it's those are called pegmatites, and that's when you have kind of large feldspar and quartz crystals. This granite, though, not necessarily porphyritic. Most of these crystals are about the same size. I mean, some of these feldspars here may be a little bit bigger, but that's your granite. Then you have a rhyolite, which is the same composition of a granite, but this is fine-grained or aphanitic in texture. So it erupted quickly, but it still might have some phenocrysts of quartz or potassium feldspar that started to form while it was still in the subsurface, but it is mostly fine-grained, okay? So that's a good way to identify this one. If you see this kind of fine-grained, it's lighter in color. But if you look in a hand lens, and you'll see just like a minor quartz crystal here, maybe a little bit of some darker mafic mineral that started to cool before it erupted. We call that a rhyolite, and it's almost always this light color. It can be white in some cases or gray, but generally it tends to be this pinkish color. And no real notable crystals to speak of except for these minor ones here. Then we have diorite. That's our intermediate rock that formed slowly in the crust. And that's going to be coarse-grained or phaneritic with lots of plagioclase and lots of amphibole. So not a lot of real silica-heavy minerals like quartz and potassium feldspar and muscovite. A lot more just kind of middle of the road sodium or calcium rich plagioclases, and then amphiboles, right? And it tends to have this kind of salt and pepper look, right? Kind of equal parts light and dark. And I don't know, the way I kind of remember that is diorite. Diorite is like diet. So like, and food, I think salt and pepper. I don't know. You can come up with your own. That's just my kind of silly way of remembering. And then we have andesite. That's our intermediate rock that erupted on the surface. And it tends to have larger crystals that formed before it erupted, as it was slowly cooling, of plagioclase feldspar. And then it erupted suddenly, and then this darker matrix cooled quickly. So you get coarse-grained and then large-grained, which again we call porphyritic. And so that's a pretty telltale sign of an andesite there. Then we have the mafic intrusive coarse-grained phaneritic. So lots more iron, magnesium, and calcium, so darker in color. And that tends to have lots of plagioclase feldspar and pyroxene in it. And that's our gabbro. So you can think of that as the kind of mafic version of a granite, right? Or granite is the felsic version of a gabbro. So intrusive at the high or low end of silica composition. And in this case, the gabbro is the lower end, right? So less silica-rich minerals, more iron, magnesium, and calcium-rich minerals. And then the fine-grained or aphanitic version of a mafic rock, of a gabbro, is a basalt. So dark in color, usually black or dark gray. It can have some phenocrysts of olivine and pyroxene that started to form before it erupted. But a majority of this stuff was still liquid when it erupted on the surface, so it formed very quickly. And that's how you get a basalt. And to tie this in with plate tectonics a little bit, basalts tend to be the rock that forms most of the oceanic crust, whereas granites and rhyolites tend to be the rock type that is present in most of the continental crust. Then we have obsidian. That's the next one in your group. That is dense and glassy. Didn't form any crystals at all. That's that frozen liquid, and pretty distinctive. If you get a black, shiny glass rock in your test, that's obsidian. Then you have the glassy ones that get blown apart in an explosive eruption, tend to be felsic to intermediate. They have lots of vesicles in them, and these cooled in the air as that magma was being blown apart into small fragments, and that forms the rock in your kit called pumice. And most pumices, if you wanted to test this, you could drop it in a beaker full of water, and a lot of times pumice will float. So it's a floating rock because of all those air bubbles in there. And then the more mafic version of that is a scoria, and that's vesicular as well, so it's got those bubbles, but it's darker in color, and because it's mafic. So let's talk a little bit about how rocks melt. So when rocks are solid, they have these nice ordered structures here. And as you start to heat them up, some of the more weaker bonds between certain atoms or elements start to break apart, right? Because you have to introduce energy into a system to break a bond, right? It requires energy, just like the boiling water example that I used. As that starts to happen, you start to get a breaking of bonds, and that's essentially what starts to form a liquid, where you get smaller constituents of this solid framework broken up into pieces, so they're able to flow past each other because they're not bonded together anymore, and that's what forms a liquid. And the different components that I want you to commit to memory for how a rock melts is obviously heat, right? We introduce heat. Heat breaks bonds, and then elements slide past each other and are essentially in the liquid phase. And that should make sense. You know, you take ice and heat it up, it forms a liquid. You take iron and heat it up, it will become molten. You take a granite and heat it up, it'll eventually become a rhyolitic lava. We also have pressure. As you increase pressure, in this case, you get a solid, okay? So you can have rocks deep down in the crust, or actually the mantle is a great example, right? Remember I told you the mantle is it's squishy, like a slush almost, right? It's not quite a liquid, it's not quite a solid, it's sort of halfway between, even though it's super duper hot, much hotter than anything in the crust. But because it's under so much pressure, it's a little bit more like a solid than it would be if it was at a lower pressure closer to the surface at that same temperature, right? And so increasing pressure favors a solid, but a sudden decrease in pressure causes a liquid. And that's closely tied in with volatiles and gases that are in a rock or in a mantle product. Volatiles and gases tend to get in there and relieve pressure, right? So if you introduce a volatile or a gas into a really, really, really hot mantle rock that's under a lot of pressure, that will relieve the pressure suddenly, because now you've got gases in the mantle, and so the more dense material, that is the mantle rock itself, will preferentially want to move into that place where there's lower pressure, those little bubbles, and that decreases the pressure on the mantle overall in that region, if that makes sense. And that can cause a mantle rock to suddenly liquefy or melt. So let's think about what this looks like on this phase diagram here, where we've got time or temperature 0, right? So that'd be cooler, and temperature is increasing as we get to, say, T4, temperature 4 over here. So at some pressure, let's say P1, which would be closer to the surface than P3 down here. At P1, at cooler temperature T0 and cooler temperature T1, this rock is solid. Then, as we increase temperature at the same pressure, then we get to T2, and now this rock has become liquid, right? And keeping pressure steady, as we go up in temperature, it stays a liquid and just becomes a hotter and hotter liquid. And then we'll increase pressure, so we'll go deeper into the crust. That's P2. At temperature 0, 1, and 2, this rock is solid. And then when we get to T3 and T4, it becomes liquid. And then at our highest pressure here, P3, so this could be in the mantle or really deep in the crust, that rock will stay solid as the temperature increases, and it takes a lot higher temperature for it to become a liquid to overcome the effects of the pressure. And we call this line here, and it has a relative slope based on our temperatures and pressures here. We call that the liquidus or solidus line. And we call it a liquidus line when we have a rock that is solid and we want to talk about when it turns into a liquid. We call that the liquidus line. And if we're approaching it from the other side, where we're looking at a magma and we want to know when something's going to cool and it crosses this line, we call it the solidus line here. Okay, so that's just a matter of your perspective and your approach and the questions you're trying to answer. So how do we melt A or C? So if we wanted to melt A, and it's at a given pressure, right? It's not, we're not raising or lowering it as far as pressure. We're not moving it closer to the surface or moving it deeper into the crust or mantle. The only way to melt that is to increase the temperature. And then C, same thing. It's a deeper rock, so it requires a higher temperature. Notice it's solid here at A, and then it becomes B at this temperature range. But that same rock, deeper, so higher pressure, same temperature, it's going to be solid, and so it requires more temperature to get it to D here, where it's at the same pressure, but you have to increase the temperature to get it to D. And then, so that means if you have a rock that's at the same temperature, but it has a change in pressure, it can also solidify or melt. So you see here, B and C are at the same temperature range, but they're at different pressure ranges. And so that can also cause a rock to melt or solidify. And a magma intruding raises its temperature. That's the least common. A raising temperature above the rock's melting point is how you get it at the same pressures, like I said. And a magma intruding raises its temperature. So you can get a magma that intrudes in, and as it's interacting with the crustal rock that it's intruding into, if that magma is hot enough, it can start to melt that rock, okay, and incorporate it into the magma as it moves through the crust. And That's how we get higher silica rocks in continental crust, because that magma is moving through. It's raising the temperature of the rock it's moving through, and some of that rock melts into the magma. And since crustal rock is mostly composed of silica-rich felsic rocks, that magma, once it erupts on the surface, will also be felsic. So again, as I said, with pressure, we have to remember that temperatures within the Earth are really high, right? But as we increase pressure, that reduces the ability of a rock to melt. So you can get rocks at depth that are really high in temperature, but are still solid because of that pressure. So as you decrease pressure, you decrease the melting temperature of the rock. And so it will start to solidify. Here's an example of that. So if we had a mantle plume, right, a hot spot or a divergent plate margin, we get that rock rising up closer to the surface. And it's under pressure and it's hot. It's mantle rock, right? It's hot, but it's under pressure, so it's fairly solid or solid-ish. And then as it rises up to the surface, it has a decrease in pressure at the same temperature, and so it will melt. And we call this kind of melting decompression melting. And here's a diagram from one of your textbooks illustrating that. So here we've got mantle rock. It's pretty much solid. It's a peridotite. It's not quite solid, but it's pretty solid. And then as it moves up, because it's hot and more buoyant, think of our lava lamp example that we use. We start to get partial melting of the mantle, and that's when we start to see quartz and things like that start to become liquid, and those lower temperature minerals are still liquid. You might still have some solids in there, the more mafic minerals. And then as that rises up, it starts to melt even more and more and more as that pressure releases. That's what causes the split at this divergent boundary here in the oceanic crust. And we can have a magma chamber that just kind of sits there, or we can have lavas that erupt on the seafloor. This magma chamber here would likely form a gabbro, and then when it erupts on the surface as a liquid, it would form a basalt. So this is an example of decompression melting, where temperature is fairly constant, but pressure is changing. And then if we introduce volatiles into a mantle rock, like a peridotite, then we also get melting. So as you add volatiles like water or carbon dioxide, that decreases the melting temperature of the rock. So if the temperature stays the same, but you introduce volatiles, if you're keeping temperature steady, that will lower the melting temperature, and so you'll get some melt at that temperature. And this is, like I said, closely related to pressure. Volatiles and gases relieve the pressure in a system. And we can see here that at low temperature and low pressure and low temperature at high pressure, we've got solids here, right? And then you introduce a volatile, and it's basically taking this liquidus line and it's moving it over to a lower temperature here. So in this space here, we've got melting. And so one thing to notice is under high pressures, we've got a higher temperature range where the melting point is sufficient for the rock to melt. So we see this in subduction zones where at deeper pressures, right, higher pressures at deeper in the mantle, those volatiles activate the melting process at greater depths. There's a higher range of temperatures that you can be at deeper pressures to get melting. And what that looks like in a subduction zone is you've got your oceanic crust here coming down, subducting under this continental crust. And those volatiles are not melting the mantle until you get to a certain pressure where it's a little higher pressure. And for whatever reason, that causes melting. You guys don't need to really concern yourselves with that per se. That's a little higher level. But when that happens at this certain range, you get melting of the mantle rock, and then that stuff comes up and will either solidify as a pluton, in this case a granite, right, in this magma chamber here or in this magma chamber here, or it'll erupt onto the surface as a felsic rock. So it's more mafic down here when it's mantle rock, but as it's moving through this crust, it's picking up more silica and solidifying out more olivine, pyroxene, stuff like that. So once we get up here, we have a much more felsic magma body or felsic eruptive lava. So in summary, heat raises the temperature above the rock's melting point. Pressure decreases the melting temperature of a rock. And when that happens, we call that decompression melting. And then water volatiles reduce the melting temperature of the rock, and we call that flux melting. So one thing I really want to point out here, and here again is the Bowen's reaction series that we saw in the minerals lecture. And one thing I want to point out is that you can get different magma compositions that can be derived from a common magma. So you can get a magma that's completely liquid and it has all of its ions in it. It's got a bunch of oxygen and silica, but it's also got a bunch of iron and magnesium and calcium and potassium and aluminum and whatever. And again, as that magma is cooling, at first it's going to start to form olivine and calcium-rich feldspars, right? Those are your ultramafic rocks. Then a lot of that magnesium and iron and stuff is being used up. What's left will incorporate itself into pyroxenes, amphiboles, and biotites, and plagioclase feldspar. And then as that magma continues to cool and rise up through the crust, then we start to get more amphiboles, biotites, and more sodium-rich plagioclase feldspar. And then finally, at the lowest temperatures, that's when we get the potassium feldspar, the muscovite, and the quartz. So one magma at the very top here, before anything started to crystallize, was just a magma with a bunch of elements in it. And then as it cools, its composition will change. And at this point, we would call this an ultramafic magma. At this point, we would call it a mafic magma, intermediate magma, and then felsic magma, right? So same magma at the beginning, but then as things start to crystallize and cool, there's just less elements for that magma to use as it cools, so to speak, to form new minerals, and that's why we get mostly silica by the end. Because again, remember, silica is the most common element on Earth. And we see that minerals that form in the same general temperature range occur together in the same igneous rock. So usually rocks that have a lot of olivine in them also have pyroxene and calcium-rich plage. And then minerals that form at the lowest temperatures, where we see quartz, we tend to also see muscovite and potassium feldspar. So I want you to think about, would we see olivine and quartz in the same rock? And the answer is generally no, we don't. If this cooled very slowly and is at a low temperature, the olivine has already dropped to the bottom of the magma chamber when it was cooling, when it was much hotter. And the same with the plagioclase feldspar. So that emplaces a bunch of olivine and calcium-rich feldspar at the bottom of the magma chamber, but that magma is continuing to rise, right, as a liquid up through the crust. So as it does, it's either melting more crustal rock and getting more silica, or it's forming these kind of intermediate minerals and mafic minerals. And as it rises up, eventually, once it gets closest to the surface of the crust, all that stuff, all these minerals have already been deposited lower in the crust and left behind while this stuff is still rising. So by the time you get to the closer to the surface, you pretty much just have quartz, muscovite, and potassium feldspar. So the olivine has long since been left behind, and so we don't see quartz crystals in a rock next to olivine crystals, hardly at all. Maybe in special cases we might, depending on whatever tectonic regime we might be in. There could be some weird mixing and stuff there, but generally speaking, we don't see that. So during crystallization, the composition of the remaining liquid continually changes, as I said. So remaining magma at the end of the kind of cooling cycle where it's rising and cooling and forming solid minerals, we tend to see that magma being depleted in iron, magnesium, and calcium because they're the first to crystallize, and be more enriched in sodium, potassium, aluminum, and silica because that's what's left over. And we call this magmatic differentiation. And that's the chemical diversity of igneous rocks due to the process I was just talking about. So it's a change in the chemistry of the magma by adding or removing chemical components. And the three major types of magmatic differentiation that we see are partial melting, crystal settling, and magma mixing and assimilation. So for partial melting, that's what produces most of the magma in the mantle. So when it's at a deep pressure, okay, and a high temperature, so high pressure, high temperature, it's mostly solid-ish mantle rock, right? But then if we introduce volatiles or we get some kind of changes in the pressure as stuff is moving further from the core and up towards the crust or even entering into the crust, we start to get that mantle rock melting. And the first things to melt are going to be quartz, the muscovite micas, and the potassium feldspars. Those are the first to melt. And then as that pressure decreases, these other minerals start to melt. And so at any given time, you'll have different percentages of these different minerals in the magma. And so we call that partial melting because it doesn't all melt at once. It's more of a gradual process. And so the composition of the magma will be different depending on where you are in the crust. Then we have, and in that we have what we call magmatic differentiation, as I've mentioned. And basically the minerals with the lowest melting temperature, that is the highest silica, melt first, like I said. The melt produced initially has a higher silica content, so it's more felsic than the original rock. And the melt will become increasingly more mafic as melting progresses. So that means in a rock where you have solid quartz and solid olivine and all that stuff, due to the high pressures, regardless of temperature, as that magma begins to melt through a change in pressure, at first it'll be more felsic because all the quartz, all the feldspar, and all the mica has melted. But the more mafic minerals, olivine, calcium-rich plagioclase, that stuff's still solid. So the available melt for an eventual crystallization of different minerals is going to be more felsic, that is higher in silica. So that would produce those silicate, high silica minerals. And we can use this to predict the composition of partial melts. So if we start with a mantle rock like a peridotite and it's partially melted, we can use the Bowen's reaction series here to help us predict what kind of melt we might see. So whether a magma is felsic or mafic has a lot to do with the source area. So if you have mantle rock here, which is basically just a semi-solid sort of thick soup of kind of all the constituent elements that we find in the earth. So it's got a bunch of iron, a bunch of magnesium, a bunch of silica, a bunch of oxygen, a bunch of aluminum, a bunch of sodium, blah, blah, blah. If you suddenly melt that completely, you've got a magma that's rich in silica and oxygen for sure, but it's also really rich in those more mafic or those elements that make up mafic rocks. So you're gonna have a lot of iron, a lot of magnesium, things like that. So this magma is more likely and more able to produce mafic minerals because that stuff's melted and it's ready to form bonds as it cools. Okay. If you start to melt continental crust, a lot of the continental crust is composed of mostly aluminum, silica, and oxygen, and potassium. And so as you melt that, there's less of those more mafic minerals available as liquid in the melt to form mafic minerals. So as that cools, it's going to form felsic minerals. And I've pointed that out here. So, use this as you're studying or thinking about this. Continental crust melting, you're going to get more felsic and intermediate magmas. Mantle, you're going to get more mafic magmas. And what that means when you say, so we can say that like a mafic mineral contains certain elements, that's what makes it mafic, and felsic minerals contain certain elements that make it felsic. When we talk about that for a magma, what we mean is, what is that magma most likely to produce as it cools? So one is like, the source of the minerals is the magma, and if the magma has lots of silica and not a lot of other stuff, it's a felsic magma. And if it has lots of the heavier elements like iron and magnesium, it's a mafic magma, and so it will produce felsic and mafic minerals. Each one of those will. Another way that we get magmatic differentiation is through crystal settling, or what we call fractional crystallization. And what this means is the minerals that form early are the ones that form at higher temperatures. They have a higher melting point, so therefore they have a higher temperature solidification or crystallization temperature. They're denser, so they form early, and they sink to the bottom of a magma chamber, and they leave behind a magma that's increasingly more felsic, okay, or increasingly high in silica, oxygen, aluminum, and less so in the denser elements like iron and magnesium. So again, the remaining melt is depleted of those heavier elements, as those heavier elements are forming minerals and settling to the bottom. So here at time A, we just have a magma body. It's all liquid. Maybe some of it's erupting. And then as olivine and pyroxene and plage start to form, they solidify and sink to the bottom. And then as that continues, your hornblends and different kinds of plagioclase, maybe some biotite, that starts to form and that starts to sink to the bottom. And so we call that crystal settling or fractional crystallization. And so as a result, once it's all completely cooled, if you were to drill down through this, you'd find pyroxenes and olivines at the very bottom, plage, amphibole, and biotite in the middle, and then quartz and K-spar at the top. We also get magma mixing. So this is the mixing of magma of different compositions. So you can have crystal settling starting to happen, right? And so you'll get a bunch of olivine and pyroxene at the bottom of the magma chamber while the rest of this is still liquid. And all of a sudden then another intrusive body moves up through the crust and runs into this one, like you see here. And so that will suddenly reintroduce a fully melted mantle rock that's basically a mafic magma. So it will reintroduce a bunch of mafic elements into this magma body. So you could get crystal settling of olivine, and then you start to get into the intermediate minerals being settled down, right? Hornblends and biotite. But then all of a sudden this other magma body rushes in, and so then you could start to get olivine crystallizing out again, okay? Because it's just reintroducing a lot of available minerals into that magma body that weren't there before as it was cooling previously. You can also get assimilation, and this is when a magma body, like in this top left diagram here, the magma moves into what we call the host rock, which is the solid rock of the crust that it's intruding into. And it will start to melt some of that rock because it's hotter than that rock. And the minerals that have lower melting temperatures will start to move in. So in this case, you have a mafic magma that's starting to incorporate more silica-rich minerals because they have the lower melting temperature. So they're the first to melt, your quartzes and your case bars. So that will introduce silica into a mafic magma, whereas here you've got a felsic magma, right, that will suddenly get a lot more mafic minerals introduced to it. And so again, to look at the Bowen's reaction series, the way you produce basaltic, andesitic, and granitic melts basically is kind of moving up the series backwards. So you imagine a solid rock like a granite or a gabbro or something like that. As you start to increase the temperature towards melting, the first things that are going to melt are quartz, muscovite, and case bar. So that's introducing a lot of available silica into the melt, right? So it's mostly silica in the liquid part and still mafic as far as the solid minerals that haven't melted yet. Then as you move up, you'll start to get an intermediate melt where it's still got all that silica, but now it's starting to melt amphiboles and biotites and sodium-rich plage. And so that's going to give you a more intermediate melt. And then as we move up, we get more mafic as it melts the pyroxenes, and then more ultramafic as it melts the olivines. So if this, so then it, once it gets to here, it's all melted, right? And so once that's all melted, then it's ultramafic. If it's mostly melted except for the olivines, it's mafic. If it's mostly melted except for amphibole, pyroxene, and olivine, then it's intermediate. And if it's mostly melted of just the felsic minerals, then it's a felsic melt. And again, that means that the liquid portion, let's say down here at the bottom, when it's in this state, the liquid portion is just all of these minerals up top are solid. The only thing that's in the liquid would have been these minerals that melted. So it's a felsic magma or melt in the fact that if it starts to cool, whether slowly as an intrusive body or suddenly on the surface, the only elements that are in the melt that can produce minerals are, you know, heavily silica rich, right? And so we call that a felsic magma, so or felsic melt. And that means that, again, that melt is only capable of producing silica-rich minerals as it cools, whereas an ultramafic is capable of producing any of these minerals because everything has been melted into a liquid form. And so now we're going to sort of shift into plutonic and volcanic igneous rocks. So there'll be a whole lecture on volcanoes. But I wanted to talk about plutonic igneous rocks. And this is, again, where we get those intrusive rocks forming like granites, gabbros, and diorites. And plutonic just means that it's a magma chamber that's located within the crust at some depth. or maybe at the mantle crust boundary in the lower lithosphere there. And it produces these coarse-grained phaneritic rocks with lots of large phenocrysts in it, because as things cool slowly, they have more time to grow. And I'm going to talk about some kind of features, stepping away from rock types now and really just talking about some of the features of plutonic rocks in general. So when a plutonic rock is formed, we say that it's being emplaced, right? So as the magma chamber down here is producing melts that are moving up through the lower crust, which is usually generally some kind of metamorphic, super deformed, very old basement rock, we call it. And then you have sedimentary layers of sedimentary rock, like sandstones, mudstones, limestones, etc., that have deposited over that over the million years since this metamorphic rock formed. And so the magma chamber is moving, or melt in the magma chamber is moving up because of density. And when it settles in a place and starts to cool, so it stopped moving, we call that emplacement. And with sedimentary rocks, we would say something is deposited. But whenever it's an igneous rock, so any kind of magma or lava that settles in an area, whether that's intrusive here in the crust or on the surface, we call that emplacement. And once a magma is emplaced, then it stops moving and starts to cool down. And as it's cooling, it crystallizes. So that's the crystallization portion of the formation of a plutonic igneous rock. And in diagrams, that's generally shown like this. Igneous rocks are generally these kind of gray colored masses with just lines kind of going in multiple directions. That's kind of the standard. Igneous rocks, or metamorphic rocks rather, down here are generally drawn with these folds. Sandstone is usually just lots of dots. Mudstone is usually just solid brown, maybe with some lines going side, like horizontally. And then limestone, they usually make that look like bricks. So you'll see that in upcoming diagrams. But anyway, here we have an emplaced magma that is close to the surface, and that's a laccolith. Any emplaced magma that goes in between sedimentary layers, we call that a sill, and that's horizontal or parallel to the sedimentary layers. And then if it moves straight up, perpendicular to the sedimentary layer, we call that a dike. And then anything that's emplaced in the center of a volcano that's sort of like a pimple on the surface of the earth, anything inside there, we call that a volcanic neck. So slightly different than a laccolith. And then there's another larger one, and I have some slides on that, so I'll show that to you. And then the last thing, when we see plutonic igneous rocks exposed at the surface, in order for that to happen, you have to have lots of uplift and erosion. And I think I mentioned this in plate tectonics, but oftentimes as things erode, the overall weight of the continental crust gets less, right? And as that happens, there's a process called isostatic rebound, and that's where that's how far down into the mantle any particular piece of crust or plate is, how deep is that in the mantle. So as you add weight or take weight away on a continental plate, let's say, then, if you add weight, the bottom of that plate is gonna sink deeper into the mantle, and as you take away weight, it's gonna rise up. And after long periods of deposition, where continental plates have been overcome by shallow seas, you get a lot of deposition of ocean sediment. That pushes that crust, that particular plate, down into the mantle. And then when there's long periods where that is exposed to the surface, you get erosion. And as you get erosion from the atmosphere and from surface water, that plate starts to rise up. And then there's more erosion and it rises up, and then there's more erosion and it rises up. And eventually you can get some of these real deep plutons exposed at the surface. So this slide's just kind of defining the three steps again. Emplacement is magma intruding and it stops moving. Then crystallization is that magma cooling and crystallizing. Uplift and erosion is exposes the plutons. And some different physical features that we ascribe to plutons. You can have a tabular feature, and tabular just means basically not massive. So a tabular feature is a thinner feature that's usually this sill here or this dike here, okay? So tabular, I like to think of it like when they're exposed at the surface, especially dikes here, they kind of look like a mohawk, right? So they're long and thin in 3 dimensions, okay? So not very wide and long. So and a sill is that same kind of feature, but it's horizontal relative to the crust. So it's parallel to these sedimentary layers, whereas this dike is not. Massive is actually when a large plutonic body is not tabular, so it's not long and thin. It's actually, can have a number of different geometries, but oftentimes it's just a big mass. It's more like more spherical, I guess, in some weird way, or it's more shaped like a lens. And we also use the word concordant, which again, a sill is concordant in that it's parallel to the sedimentary layer. And then a dike, which is running perpendicular to the sedimentary layer, so it's moving up through it like this. It's at a 90-degree angle from the sedimentary layer. We call that discordant. And the different types we have are a dike, again, that goes up and down like this. So it's rising up towards the surface, so it's vertical relative to the sedimentary layers. You have sills, which are here. So this is a dike and a sill in one picture. You can get laccoliths, which on the previous slide you'll see that's when something rises sort of up close to the surface and it's sort of lens shaped. And then a batholith, which is like a laccolith, but it's deep in the crust. So you don't see its expression on the surface of the Earth as much, but it is a massive igneous body deep in the Earth. So again, dikes are tabular shaped. They cut across existing structures, so they don't go with the structure like the sills do, where they're parallel to the sedimentary layer. They're cutting through other layers, perpendicular. They can be as small as less than a centimeter wide, and they can be as large as a kilometer. Okay, here's and they can be both felsic and mafic, right? So as long as they're moving through the crust upwards, they can be any composition. As long as they're more buoyant than the crust, they'll move up through it. And here's a beautiful example of a dike. I believe this is in Scotland. And you can see that when it's exposed at the surface, it's a strong igneous rock, so it doesn't weather as much as whatever rock used to be here that it was intruding up through. And so that rock is long since gone, and now the dike is still remaining. So it's younger than the host rock that it intruded into, but it's much stronger, so it's more resistant to weathering. And so we see dikes exposed oftentimes when we're looking at plutonic features. We see a lot of dikes. I mean, I saw some awesome ones in Colorado, but anywhere where there's a plutonic activity and even volcanic activity to some extent, you often see these dikes exposed like this, and they look like a wall. They look like something that like a human had built. Here's another example. So here we have an ancient volcanic neck. So this would have been the inside of a volcano, so above the surface. But remember, volcanoes move up and spill material down on the sides as they erupt. That material has long since eroded away, and just the kind of massive igneous body that was in the center of that volcano that never did get to erupt and cooled slowly is left over as this volcanic neck. And then you'll see this dike over here. And this is very common around volcanoes. You get these things called dike swarms, where they're these long, sort of wall-like features. They're vertical, and oftentimes they kind of radiate out away from the volcano. And then again, we have sills, also tabular, but they follow the existing rock layers. A few are about 100 meters thick. Generally, they're much thinner. And what they're doing is they're exploiting the weakness between different sedimentary layers. So you might have a layer of limestone and then a layer of sandstone on top of that. And in between that, those sediments are compacted in such a way that they're a little bit weaker. And once magma intrudes into them, it'll preferentially want to squeeze into those spaces between those layers. And they can either squeeze into existing layers, or squeeze into existing areas, like they could get into a space that is just filled with water, or maybe a space that's filled, that's just offset by a fault. They'll squeeze in there. Or they can actually squeeze in between the layers, and as that pressure is building, as stuff is pushing up into these layers, it can actually push, or what it's actually doing is pushing a limestone layer and a sandstone layer, for example, pushing them apart and just squeezing its way in there. And then it's just a layer of magma in between two sedimentary layers, and then that slowly cools to form a sill. And they tend to be basaltic. And that's because, remember, basalt is less viscous, so it wants to flow more easily, and so it's thinner. We can think of like felsic rock or felsic magmas as kind of like spaghetti sauce, and basaltic magmas more like water. And so you could squeeze water into tighter spaces than you can spaghetti sauce in general, because it's just thinner. Here's a beautiful example of a sill that intruded into these sandstone layers here. And it just got in a space, and then it pushed its way in, and it just kept feeding down from a dike and into a sill, and it just kept pushing and pushing, and it actually separated these layers out and then cooled. And then laccoliths, they intrude between rock layers as well, just like a sill does, but they're at the surface. So rather than pushing in between two layers like this, it's pushing up on the uppermost layers of the crust. And so then it tends to not want to spread out this far, because there's not as much weight here as there is down here. So those just push way out to the side. But then like a sill right here, pushing out to the side. But a laccolith just has more force upward, because there's not as much overburden. And so it tends to form these kind of lens shapes like this. And they tend to be more felsic. Then a batholith, these are the largest intrusive bodies. They often form at the core of mountain ranges, and they can encompass huge areas, 40,000 square kilometers. They can extend several kilometers into the crust. They tend to be felsic, so they're in the continent. And when they're exposed at the uppermost portions that are exposed at the surface, kind of look like just these big igneous mountain ranges, very similar to Yosemite, like I showed you before, that half dome. Those are all batholiths. So here's a beautiful example of a batholith that's been exposed to the surface through uplift and erosion. And so these were never erupted onto the surface as they were cooling. This would have been a magma body that intruded into a bunch of sedimentary layers, or some metamorphic layers, or maybe even some weaker igneous layers. But for whatever reason, this particular magma has a much stronger rock. It's a much stronger rock type, just because of the chemicals that it has in it and the temperatures at which it formed. It just makes it much more resistant to erosion than whatever it had intruded into. So when this cooled and formed, there would have been sedimentary layers all through here, right? And the surface of the crust would have been outside of this frame. It would have been way higher than this. But as there was uplift and erosion, this stuff that formed deep in the crust slowly started to get exposed to the surface, while the layers that it had intruded into are eroding away. And so all you have left is the batholith. And it's eroding too, but just at a much slower rate. So at this particular point in time, in 2023, it happens to be exposed. But eventually this will all erode away too. And then, maybe in a million years, sea level will rise and cover all this up with sedimentary layers again. And that's just kind of the cycle that's been going on for billions of years. So this concludes the plutonic portion of volcanoes and overall concludes igneous rocks. And so I hope you got a lot out of that. And if you have any questions, please feel free to email me or post in the virtual classroom thread in our discussions. And don't forget to get after those discussion threads required for the week. One covers minerals, one covers igneous rocks, and one covers just these plutonic rocks here that I talked about in the last dozen slides or so. So I'll see you guys all next time, and yeah, have a great day.